I'm sad that I cannot see you and meet you all in person, but it will have to do this way. So today I'm going to present a library that I've been working on for a while called ZIO Redis, which is yet another Redis client in Scala universe, moreover in functional Scala universe. And to summarize, my agenda will be the following. So first, I will introduce you to Redis in case you are not familiar to it. I will explain what are the inner details relevant to client design. I will present the building blocks of Redis client for ZIO and discuss on current state of our currently supported functionality in library, as well as draft a workflow for adding more capabilities to ZIO Redis that are planned for the next couple of months. So to start over, what is Redis? In case you are not using it, Redis is an in-memory data structure store. What this means is that Redis provides a very, very broad API for storing various types of data structures like sets, sorted sets, lists, or just a plain key value mode. Besides being an in-memory data structure, Redis can be used in various other scenarios, and most frequently usages as a cache, but there's been usages of Redis as a primary data structure, basically where it mimics a database, but also Redis as a pub/sub mechanism, as well as in various clustering scenarios nowadays. Redis is by default in memories, but it provides a configurable persistent. There are, up to my knowledge, two different modes of persistent via RDB and now RLF. Check them out in case you need them, and they are broadly documented in the official docs. As of relatively recently, it provides a high availability setup via Sentinel, and it also comes with a built-in master-slave replication, which is relatively easy to set up. Besides that, Redis provides various other goodies like least recently used caching, various scripting via Lua, and already message pub/sub and classical caching scenarios. However, this is where the usual user pitch, so to say, ends. Because for vast majority of users, it's important what's the functionality and what are the guarantees provided by Redis. But for client library developers, there are more things that you need to consider. Under the hood, Redis uses a very refined protocol called RESP, which is a shortened for, which is an abbreviation for Redis Serialization Protocol. A Redis serialization protocol has the following characteristics. It's generally fast to parse. It's human readable, so it's text-based, but it's also binary safe. And usually the whole communication over this protocol follows request-response model. What this means is that client or client libraries, whether for Scala or for any other supported language, sends requests serialized as RESP chunks and expects to receive response from Redis server. Note that Redis server is single-threaded, so there are multiple constraints that you need to think over, and usual advice is to have a single connection per client, but that can be tunable up to a certain degree. You will see that I put an asterisk next to request response model because due to functionality being added to Redis, there are basically three scenarios in which this doesn't apply. The first scenario in which doesn't apply is generally known for RESP. It doesn't apply for clustering. Clustering uses a different binary protocol in order to communicate between nodes in a cluster. However, the classic request response model does not apply when using some feature called pipelining, which is basically a capability to send multiple requests and wait responses for them at once. And it also has a different semantic when used in pub/sub models. So basically, when you use Redis in pub/sub model, you basically change semantics from request response to a standard push, where client subscribes and expects events to be delivered from server side. Besides these characteristics, RESP also has some implementation details, I would say. First of all, it supports 6 different data types, which we are going to present in a few slides. Besides that, it supports on top level 2 errors. One is called error, which is basically a general anything can go wrong error, and the other one is more specialized for wrong type, which is basically emitted when you want to apply command to a wrong key. So, for example, when you try to get the length of a list for a key, which is a set. Also, each command uses carriage return line feed as a separator, and by convention, you cannot use it inside of the body or inside of the part, but just as a termination set of characters. One example of how the commands look when transported via RESP is given here. So basically what we see here is a string that starts with the first byte that's usually a discriminator for type that follows. Asterisk is discriminator for an array of values, and here we see that we will have an array of 2 values, followed by the first value, which is a string indicated by $, of 3 characters with value foo, and then a string of 3 characters with value bar. Finally, the whole chunk ends with yet another terminator. Note that this way of encoding allows for very efficient parsers, because you can basically utilize the lengths and separators to parse your data in place. Now, why this library? In Scala, there are already, I think, 7 or 8 clients that I can mention out of my head, and there are already 3 existing clients in functional Scala world, more specifically Redis for Cats, Ridiculous, and Laserdisc. However, when we started with this project, we decided not to wrap the existing clients, but rather to provide a client that is type-safe, that embraces functional programming, that is performant, which is something we are constantly trying to improve, that it has no dependency, but you'll again note another asterisk here. There is obviously going to be at least one dependency, which is ZIO. And finally, we want to make it ZIO native. So we don't want to use interrupts. We don't want to depend on a bunch of compatibility libraries. We just want to have a ZIO native library that's a single import do-it-all library for ZIO services. To achieve that, we started from the bottom up. So basically, first things we did was modeling the RESP values. As I mentioned, RESP as a protocol in its version 2 prescribes 6 possible values, which are simple strings and arrays, which we saw on previous slide. But besides them, there are also errors, numerical values or integers, bulk strings, and sort of a special values called null strings. We used a simple encoding, simple ADT there to represent all 6 possible values, and we call ADT RESP value. And the purpose of this ADT is to provide a way to serialize contents into byte chunks that will be transported over the wire, and then provide the machinery, which you don't see over the slide, which is to deserialize byte chunks received from server and rebuild the RESP values that you see. One remark I have to say here is that I have simplified the encoding from the one that's in library. You won't see a bunch of finals or privates, and the only reason I did that is for the sake of slides compatibility. Otherwise, everything would be too long and it wouldn't fit the slides. So once we have RESP values as the most low-level element of our design, on top of that, we have built Redis commands. Redis command is a simple class that is described by 3 fields: name, input, and output. As you can check out in Redis documentation, you will see that all of the commands has names, and all of them have some form of input, and they emit some form of output. As you can see, Redis command is polymorphic in input and output, and it has let's say, two purposes. First purpose is to describe commands. And second purpose is to take the input, the actual input from users, and feed it to the processing pipeline. That's the purpose of this method called run. One thing to note here is this is the actual main interaction point of users with our library. However, you also see that Redis command is private, and it has a fixed amount of instances, which is basically the functionality that we support, and we are going to go through the idea a bit later. Now, let's focus on these two somewhat strange elements called input and output. Input is basically an encoder of user data. So whatever you submit will be transformed into REST values by passing through input. As you can see, input exposes a single method called encode. It's polymorphic in its input type. It's basically a GADT, and it produces a chunk of bulk strings that's going to be sent over the wire. I've given one example of an input, which is long input. It basically just extends input and provides an implementation of encoding, so converts this long into a proper REST value. But we also have a bunch of other terms, for example, string inputs, Boolean inputs, no inputs, and many other tuple combinations, as well as non-empty list. Basically, I think at this point there are between 25 and 30 various terms that describes all of the possible inputs we have on Redis commands. On the opposite end of processing is the decoding part that we called output. Output is also polymorphic in its result type. It exposes two methods. One of them is a final method. It has a fixed implementation where it basically just matches over a REST value and provides some data A. And on the other side is a try decode method, which results in a type A, and it's fed a REST value. Note that the signature of this method implies unsafety, and in the essence it is unsafe. It doesn't use any effect system under the hood. It heavily relies on throwing no stack trace exception, and it doesn't allocate as much as possible. The reason for this choice is obviously performance, but also know that these exceptions that are thrown internally are suspended on the higher level in command, so none of them will leak and result in fatal error. Similar situation as with inputs we have in output. So we basically have a bunch of terms that describe various kinds of output that we have in ZIO Redis. There are fewer than inputs, but still I think there is about 10-ish of them. One example is a long output that we see here. And finally, how to interact with it. We have something called instances. Basically, these are instances of commands. As you can see in a companion object, I have split an API per groups of commands as in Redis documentation. So there are keys, connection sets, etc. Here we see an example of a keys API that has an instance of a command called get, which is a Redis command that accepts string output and that can result in an optional output, which is a multi-string, meaning chunk of strings. And above, you see a get method, which is a principal point of interaction that user will do, that just delegates to the run below. So what this run will do is it will submit the input fed by user, this key, to the whole execution pipeline. To see them in action, here we see one example from our integration tests where we basically generate two set identifiers, first and second, and then we invoke set addition to add set members to first set, which are A, B, C, D, to add set members to second set, which is A and C, and finally to calculate a diff between sets, first and second. Assertion is afterwards straightforward. Once we have all of that in place, we invoke run, and run invokes something called CommandExec. CommandExec is the main workhorse of ZIO Redis. It maintains two communication queues, so one for outgoing and one for incoming data. Basically, these queues are just two fibers that are racing with each other infinitely, and once command submits itself to as executor, it's enqueued, and later on it's taken from the queue and asynchronously completed via promises by the incoming queue later on. How to use it? Let's show us very simplified example of how you can use ZIO Redis. First thing, you have to obviously design your service. Here we have a simple service that will check set membership. It follows the recommended module pattern, and as you can see, it will later on invoke as member function, and here it will die on Redis errors. You can obviously take another approach of handling it. This is for simplicity, and it will provide some environment, which is, as you can see, consisted only of Redis executor. Once you have your code in place, you have to configure it somehow. Obviously, you need to fill in your application conf. I sincerely hope you won't fill it this way as I did on slides, so it will probably come up from some environment variables. But once you have that, somewhere in your main, you will have your config loaded, and then you will wire up the Redis executor layer. Note that there is a logging layer required here. In this example, I just ignore it. Basically, it will produce no results, but in general, it's an advisable thing to do, to provide it as well as with configuration, and then feed the Redis executor live layer, which will create a connection to the cluster and initialize all the queue and start that consuming process that I mentioned moments ago. One important question is, how fast is it? We went through two encodings so far. First encoding was extremely fast. It was comparable with fastest Java libraries at the moment, but it was very unfriendly to pipelining and very prone to some edge cases. So we changed the encoding to more utilize ZIO streams, more precisely syncs, which reduced our performance quite a bit, but it's still, I would say, decent. So for example, for a benchmark that fetches 500, that do 500 single keys lookups, it's slightly better than Ridiculous and Laserdisc, and a bit worse than Redis for cats, which is the behavior that we got in the similar benchmark, which is for updating 500 keys. However, we have more or less identified the performance bottleneck, and I think we will, once that's removed, we will get either comparable or better performance than Redis for cats. Also, I expect that we will benefit from migrating to new ZIO streams encoding relatively soon. Currently, we support a vast majority of Redis API, at least prior to version 6. So APIs like connection, geolocation, hashes, various sets, keys, lists, etc. are already supported fully. We are constantly adding the diffs that are introduced in Redis 6, and we have an open ticket to support all of the new functionality that came with Redis 6. There is also quite a few of in-progress tasks. I would say that the priority of tasks is exactly as listed here. So currently, partially supported is something called test executor. As you see, we've shown how to wire Redis executor that connects to cluster, but we also started to build a test executor that will work on top of ZIO STM and provide an executor behavior that's completely in memory and detached from Redis. At the moment, test executor is capable of responding to all connections and sets functionality, and I am hoping that in the next 2 weeks we will get full coverage or full feature parity with normal executors, so that you can write your tests without the need to spawn additional infrastructure. We are working a lot on tuning the performance. As I mentioned, we identified quite a few bottlenecks with deserialization mechanism. This is an ongoing thing, and there are a couple of benchmarking tickets that everybody is welcome to join. And there is also a transaction DSL that will land soonish, it will support transaction capability of Redis. On recent ZIO hackathon, we started work on PubSub and clustering. This is going slowly, but these two functionalities are A, quite big, and B, they are, I would say, not as important as the previous three. As you can see, there is quite a lot of activity, so I would have a plea for all of you to join, because there are quite a few open tickets, and it's quite interesting to challenge both performance stuff and general usability concerns. My plan is to have snapshot releases done today, so we will have first usable version of ZIO Redis, and first stable release I expect to follow until the end of the week. Last but not least, I'd like to thank to certain people that participated in the development so far. First of all, thanks to John for all the help with designing this library and refining all the concerns. Besides him, I want to thank to all my co-maintainers, Alexander Novakovic, Alexander Škrbić, Laklan Odi, and Maxim Šuvalov, as well as to all contributors, both regular ones and the ones that just started contributing during the recent ZIO hackathon. Last but not least, I'd like to thank all of you for attending the talk, and for today, I will wrap it up. Thank you very much.